So playing around with graphs of sinusoidal functions, sine, cosine. We'll take a look at tangent next time. We had to think back about transformations of functions we learned back in pre-calculus part 1. And so we have the horizontal transformations. That's when we multiply something on the outside of a function or we add something to the outside of a function. And they're pretty straightforward. If a is greater than 1, we're going to get a stretch vertically. If the addition k here is positive, it's going to go up. However, when we do the horizontal transformations, that means on the inside we add or multiply. It's exactly backwards of what happens with those vertical transformations. So let's take a look at an example. Suppose we had the function y equals 2 times the sine of pi times x plus 1. So I want to know what this looks like. So I just want to first, before I graph it, I just want to make a prediction about it. So this 2 out front, multiple, is going to make something bigger or smaller. It's outside, so it's bigger. It's exactly what I expect. This should be a vertical stretch. The pi multiple on the inside here, that's horizontal because it's with the x, so it's going to be a horizontal change. And it's going to be backwards of what happens with a vertical because pi is greater than 1, so that means it's going to be a compression. And then I have this 1 on the outside. It's outside, which means it's vertical. And it's a plus. Vertical stuff is pretty straightforward, so that means it's a vertical shift up. All right, so let's see what's going to happen. Now, the original sine function, sine of 0 is 0. That's a good point to know. So 0 inside here is still going to be 0 times 2 is still 0, but then there's going to be a plus 1. So again, as far as vertical and horizontal goes, that doesn't change 0 much, but the plus 1 does change that. It's going to move it up 1. So I'm just kind of trying to get wrap my mind around what this looks like before I whip it into my calculator. So instead of starting here at the origin, it's going to start up higher. So its center line, instead of y equals 0, is going to be y equals 1. Just going to draw a dotted line there. Now, the sine function used to go up to 1 and down to -1 from its midline, and I've just doubled that, so it should go up 2, down 2 from the midline. So if that's the center right there, it's going to have a peak instead of 1 above. So if that's 1, 2 would be here. It's going to have a peak that's 2 above that midline. So up here at 3, I'm expecting to see a peak. And then remember, it's going to come down and hit its midline, and then it's going to drop down. So let's see, double that out there. That's the middle there. It's going to drop down from the midline 2 units to -1. So I'm predicting there's going to be the bottom of it there. So it's going to be something like this. It's going to rise up taller than it used to be. It's going to come down through its midline, and then it's going to rise up again. Now, it used to go over here to 2 pi to get a full wave and pi to get a half wave, but I'm compressing by pi, which basically is a division. So because of the pi up there, instead of having a full wave at 2 pi, if you divide that by 2, the pi's divide out, so it should form a full wave at 2, a half wave at pi divided by pi, which would be 1. So that's my prediction here. I'm going to get a full wave from 0 to 2. It's going to live between 3 and -1 for y, centered at 1. And instead of starting its waving at the origin, it's going to start at 1 because of the vertical shift. Let's graph it, take a peek. Desmos was pretty nice earlier. Let's delete some of this stuff. Okay, so I'm just focusing on the sine. So here's my original sine function. I'm going to turn this one off for a minute. And then what do I want to have happen? I want there to be a 2 on the outside of my function. And I like to put the times in, but that's optional. And then on the inside, I'm going to do a pi times x. And then on the outside out here, I'm going to do a +1. Let's see if that matches my prediction. Turn it back on. All right, so my claim was that I would get a full wave right to 2. Let's turn off the sine for a second so it's not so messy. I claim the center line of this thing is y equals 1. Let's graph y equals 1. Yeah, that looks like it's going right through the middle there. And a full wave on this thing right here. Let's zoom out, in. There we go. Move you over. A full wave, so if I start at the center line here, a full wave is what I get. I'm going uphill through the center line. One full piece of this wave is when I go back up through the center line, and there I am at 2. Now, that chunk of the x-axis that gives me a full wave, that's called the period of the function. So basically what I could do is I could make a rubber stamp. Let me go back to my notebook for a sec. I could make a rubber stamp of this part right here. Out of the way, zoom. So turn that into a rubber stamp. And I just keep stamping that over and over again, and that's my function. Okay. So that the width of that stamp is your period. So I would say for this function has a period of 2 because that's the length horizontally I need to get one complete wave. So this function is period 2, and period is the horizontal distance for one complete wave. What's the smallest chunk of the graph that repeats? That's the period. So here the period is 2. If we look back at the original sine function, turn that one off and this one on. This one here completes a complete wave from 0 all the way up to this point over here, which is 2 pi. And you can pick the period in different ways. So for example, I could start from this minimum point here. When do I get to a minimum again? So here I am at -pi/2. I get a minimum again over here, which is at 3 pi/2. So the distance from bottom to bottom horizontally is 3 pi/2 minus -pi/2, which gives you 4 pi/2, which is 2 pi. So no matter which 2 points I pick to try to find a complete wave, I'm going to get a distance of 2 pi. So if I picked this point right here, I'm going downhill through the x-axis. When do I go downhill through the x-axis again? The nearest place that happens is right here, downhill through the x-axis, and that's a distance of 2 pi. So no matter what, the period of the sine is 2 pi. Doesn't matter where I start counting that horizontal distance. Let's look at the cosine for a sec. Cosine, you could say, if we think about the y-axis here with as our starting point, the next time we have a peak is way over here, and that happens to be 2 pi later. So you can see the cosine also has a period of 2 pi. Very important. Let's make a note of that. So these sinusoidal functions are called periodic functions. Hang on, my cat's knocking on the door. There you go. So periodic functions, and the definition of a periodic function, a function is periodic if f of x equals f of x plus p for all values of x. And we definitely have that happening. And that's what I was demonstrating in my pictures earlier, but using a different way to talk about it. So for example, I get 1 exactly 2 pi later. And if I look at when 1 occurs again, it's another 2 pi later. Whoa. Oh, help. Didn't mean for that to happen. That was cool. If I picked on this point right here, I'm going to get exactly that y value again, exactly 2 pi later over here. Close, but not exactly. It's hard to pick a point. It's exactly that same distance, but that's the essence of this function right here. So let's just make something up. So I was trying to find, let's say I was using g there, g of 1/2, let's say 0.5. And I get a y value of 0.87758, blah, blah, blah. My claim is if I add 2 pi to that, I'm going to get exactly the same y value. So what is g of 0.5 plus 2 pi? Get exactly the same y value. And it doesn't matter whether I start, if I look at 0.5 or 0.7 or negative 0.3, the y values will match if I add on a 2.5, just because of the nature of the sine and the cosine. So they are periodic functions, and their periods at first are pi. So both sine and cosine have a period of 2 pi. We can alter that period by making a multiple of x, so changing the period. If I look at, for example, the sine of a times x, remember, this is going to be a horizontal spectral compression depending on whether a is positive, sorry, a is a proper fraction or an improper fraction. So it's backwards of what we think, though. So if a is something like 2, is going to increase the period, decrease the period, it's going to shrink it. And if a is a fraction like 1/2, it's going to increase the period, it's going to stretch it, right? So we have that backwards thing for a. So the period of this function right here, instead of being 2 pi, is going to be 2 pi divided by whatever number a is. So for example, earlier, we looked at the function where we had a pi times x. And so my claim, according to this relationship, because of the backwards effect of horizontal transformations, that's going to be 2 pi over pi, the pi's divide out, and I'm going to get a period of 2. And remember, we did see a period of 2 at that function in a previous example. If I did something like looked at the sine of 1/2 x, then the period for that one would be 2 pi over 1/2 multiplied by the reciprocal, 2 pi times 2. I should see a period of 4 pi. So the wave isn't going to repeat itself until 4 pi from some starting point. Let's verify that. All right, go away, go away. Turn on the sine function. So that can go away too. And that can go away. So I'm just going to type in sine of 1/2 times x. And I can see it is definitely stretched out. And let's change that color to green for comparison. So the green is the stretched out one. I have 1/2 times x. And what does the period seem to be? So again, the green function is going uphill through the origin. When is it going uphill through the x-axis again? and it's not till way over here at 4 pi. So there's that period of 4 pi. We could double check using the peak of the function. So let's move this out of the way and slide this over. And can I see the peak? Yeah. So here's the peak somewhere over here at pi 1. The next peak to the left is over here at -3 pi, and the distance horizontally between those peaks is 4 pi. So when we're trying to figure out how long is it going to take the sine function to repeat itself, that's called the period. And the period is changed by multiplying some number by x. And the new period is always going to be 2 pi divided by that multiple, right? Because we're doing a horizontal transformation, so it's backwards from what we expect.